All right, everyone. Today is part 2 of the lecture from either Thursday, the 9th of March if you're in 4th period, or Friday the 10th if you're in 5th and 6th. The first half I spent showing you how we could apply some math, or aka solve the circuits that are arranged in series. And so that, of course, just means I want to find all 4 variables, VIRP, for every component in this circuit. One of the ways I showed you could do this is to organize your thoughts in what's known as a VIRP table, which is simply a way of finding all 4 variables, voltage, current, resistance, power, for each thing, and organizing your thoughts neatly. A couple of things that I wanted to point out about how this works. I asked you to take a look at this circuit. We have a 3 ohm and a 1 ohm resistor arranged in series with a 12-volt battery. And the first thing I wanted to point out is, as far as which one should be brighter, well, every single electron that comes out of this battery has to go through both of the light bulbs. And so every light bulb is going to get the same amount of current, the same number of electrons. What'll be different is that they will spend their energy differently according to how difficult it is. Because this guy right here is harder, he's going to get more energy. You would spend more energy on a hard test than you would on an easy test. And that plays out down here. Resistor B, with its big resistance, got 27 watts of power. Resistor A, with its smaller resistance, only got 9 watts of power. We could also notice that because it's 3 times harder, it got 3 times more voltage, and since the currents are the same, that means it got 3 times more power. So in series, the harder one is going to get more energy every second and more energy per every electron, because every electron has to go to all the light bulbs, and they'll spend a bigger share of their energy on the hard one. So I asked you to do this one on your own in class, and what we saw is that even though these 3 have different resistances right there, the current's going to be the same everywhere, because where else could you go? If you were trapped in these wires doing laps around the circuit like this, you have to go through each of, well, I guess my drawing didn't actually go through it. You have to go through each of these light bulbs as you go around the circuit, because there's no other path. So the current's going to be the same everywhere. What's going to be different is the amount of voltage it's giving up. And because this is the hardest one, because this resistor has the most resistance, the electrons will have to spend more of their energy per electron and per second getting through it. So he'll be the brightest, and this one right here with the smallest resistance is going to be, this guy right here is going to be the dimmest, the not brightest. So that was a review from last time. What I want to do with you all today is see how these rules are going to work out for a parallel arrangement. The electricity here is not constrained to go through both of the light bulbs in one lap. The electrons are going to choose. Now, some of them, I'm going to try and color code this, some of them are going to choose to go on this path right here, all the way around the light bulb, or all around the circuit, and others are going to choose to go on this path as they go around like so. And either way, what you're going to see is that each electron only goes through one bulb. So the electrons only see, I'm going to see this thing in quotes, they're only going to see one resistor per lap. That's one rule. The second rule is that the electrons still have to give away 100% of their energy per lap. So I'm going to start by filling out my VIRP table with what I know. It says it's a 10-volt battery, and it says resistor A is 20 ohms and resistor B is 5 ohms. We need 2 numbers in a column. And in series, this was really easiest for us to start. Here, let me just back up a sec here. In series, we knew exactly where to start this thing because you were given a bunch of information, right? So in this series circuit, we knew that A had a resistance of 3, B had a resistance of 1, and C had a resistance of 2. We didn't have 2 numbers, but what you were able to do is say, hey, every electron sees 3 ohms, and then 1 ohm, and then 2 ohms. And so every electron that went through here saw the sum of these 3 numbers of resistance because they all did all 3 light bulbs. In parallel, that ain't the case. I absolutely positively do not want to see any of you tell me that that's 25, right? It doesn't work that way. Draw one loop out of this battery and through a resistor and back home, either the yellow or the blue. You don't see it go through both. You do not see one single loop that goes through both resistors and the battery on one lap around the track. So what we can do in math class is say that plus is the same thing as and. If you go through resistor A and resistor B and resistor C, that means that the total resistance you went through was 3 and 1 and 2, or 3 plus 1 plus 2. That's why we were able to easily say there was 6 ohms of resistance total in this circuit. In parallel, that ain't the case. You think back to when I beat whoever it was that I raced against. gosh, I'm getting all my classes mixed up now, with the drinking thing of the drinking water through the straws, or when I had you all go out and run through the doors. Having these branches in parallel with each other gives the electrons options about whether they're going to go that way or whether they're going to go that way around the circuit. All right, so you're not going to go through one and then the other. You're going to go through one or the other. All right, and so if we think about the math here as plus being and, the math for or is something really weird and really different. You don't know what that is yet. That's what's going to come on Tuesday of next week. The math for or is not plus. So do not tell me that's 25. We won't be able to use that bit of logic. We won't be able to solve for what the equivalent resistance is yet. So what we can do, though, is to get more numbers in the cells, is to realize that every electron that leaves this battery just goes through one light bulb. So they have to get rid of all 10 of these volts right there, which means that they're going to spend them on whichever light bulb they see. So if you take the blue path, in fact, let's even color code this a little bit. Resistor A is the blue path, and so I'm just going to color code this column blue to match it. Resistor B, I colored yellow arbitrarily, so we'll make that one the yellow path that looks like so. When they go on that blue path, they only see one light bulb, and so they're going to spend all 10 of their pieces of energy on that one light bulb. Similarly, if they choose to go through this path right there, they're going to spend all 10 of their pieces of energy on that one. Well, you've got two numbers in a column now. Remember, our equations right here, I is current is voltage over resistance, and power is voltage times current. The equations let us easily figure out what these current values right here ought to be. So V over R, 10 over 20, we have 0.5 amps, and 10 over 5, we have 2 amps right there. That's a grand total of 2.5 amps of current coming out of here. Now, this should make a lot of sense to us. All right, A is 4 times harder than B, right? This is 20 ohm difficulty versus 5 ohm difficulty. A is 4 times harder. If you asked every kid in the school to choose, hey, do you want to do a hard thing or an easy thing? More are going to choose the easy thing. So if A is 4 times harder, that means B is going to get 4 times more electrons because it's easier. More people will choose the easy thing. We see a ratio of 4 to 1 here, and we see a ratio of 1 to 4 there. Those ratios should just be opposite of each other. The harder it is, let's say it was 10 times harder, then the easier one would get 10 times more current. All right, we also now have the ability to solve for power. So power is voltage times current. So 10 times 0.5 is 5 watts right there. Oops, I guess I didn't mean to erase that part. And 2 times 10 right there is going to be 20. Again, we expect to see that the one that is easier should get more current flowing through it. That is the complete opposite of what we saw up here in series. In series, the harder one gets more power because everybody has to go see it. All the electrons have to go through all of them, so they budget their energy and they spend more energy on the one they want. So up here, resistor number A gets most of the energy from every electron. Down here, the harder one gets all of the energy of less electrons. This one right here, because it's harder, because fewer electrons choose to go to it, doesn't get as many electrons coming by and handing it energy. Therefore, its power is going to be weaker and it's going to be a dimmer bulb. Complete opposite situation. As far as filling the rest of this out, I'm going to be able to use this equation and solve it for R. So multiply R onto each side, divide I out from each side, and resistance equals voltage over current. So 10 divided by 2.5 means my resistance is 4. Now, a couple of things I want to point out to you. Right off the bat, this number is smaller than either of those, and it should be. Drinking through 2 straws is easier than drinking through 1 straw. Getting a crowd to go through 2 doors is easier than getting a crowd to go through 1 door. Having 2 cashiers at the supermarket is easier than having 1 cashier. Having an extra lane on a highway means more cars can flow. This number right here, this equivalent resistance in parallel is always going to be smaller than the smallest. So if you have, say, 3 resistors in parallel, whichever the littlest one is here, this is always going to be less than the littlest one. I don't know what this number is going to be yet here, but looking at 2, 6, and 4, I can guarantee you that that's going to be less than 2. As far as how much less than 2, we'll figure that out in a minute. We'll get back to how to solve that equation here in a bit. So you have the ability then to solve the rest of this. 10 times 2.5 is 25. And we can check if this works out pretty easily. The voltages should be the same everywhere because everything that the battery gives is either eaten up by this light bulb or eaten up by this light bulb. The currents have to add up because if 2.5 electrons come out of the battery every second, some go this way, some go that way, they can't get lost. The total amount of electricity flowing in the circuit has to be constant. The resistance is kind of weird here. This is, again, you don't know what the math is for OR. This is not adding them up. It's going to be something else. And please don't tell me that it's 20 divided by 5. This would be 4, even if I flip-flopped these. Even if I put A and B as different numbers, it would still be 4. It's just a coincidence that 20 divided by 5 is 4. And whether you do series or whether we're looking at light bulbs in parallel, the total amount of power has to add up to whatever the battery provides. Okay, so what I'm going to ask you all to do on this one, in this case, they're going to have different amounts of current flowing through them. More will travel through the easier one, but they're still going to get 100% of the voltage from each electron. So this easy guy right here is going to get all the energy from more electrons. The hard guy is going to get all the energy from less electrons. That explains why. I'm going to ask you all right now to do this one on your own. So right now, go ahead and pause this. Yep, I'm going to ask you to pause this one and try your best to fill this out. Once you've got this thing done, then you can unpause and see if you're right. All right, so ready, set, go. Pause. Okay, so I'm going to fill mine out here, and you're going to see if you did yours right at the same time. I know that these voltages have to be the same everywhere because whether I choose, let's just color code this, whether I choose this loop or whether I choose this loop, let's see, that would be B right there and A right there, or whether I choose this loop coming all the way around like this, right, you're going to spend all of your energy that the battery gave you. So since on these loops there's only one path for the electrons to go, the voltage will be the same everywhere. Well, I can also use I is V over R. So 24 divided by 4 means there's 6 amps going this way. 24 over 6 is 4, 24 over 2 is 12. This should make sense that the easiest light bulb gets the most current and the hardest light bulb gets the least current because more people, not 100%, but more people are going to choose the easier test. 4 plus 6 plus 12 I can do in my head is 22. 22 electrons come out of the battery every second. 4 go that way, 6 go that way, 12 go that way, but that has to all be added up to 22. So oh my gosh, I'm going to have to use a calculator for this one right here. I'm not trying to make a mistake. So 24 times 22, that means that this battery is giving out 528 pieces of energy every single second that goes by. And 288 of them are being given to this really easy resistor, and 24 times 12. 24 times 4 is 96 of them, right? 24 times 4 is 96, are going to be given to the really hard one, and the rest, 24 times 6, 144, are going to be given to the medium one. What you'll notice is these three all add up to 528, right? Every single piece of energy that the battery gives out is going to be eaten up by one of these 3 light bulbs right there. As far as finding out what this resistance value is, we already know that it's going to be less than the least. It's going to be smaller than any of them because this circuit by itself, just this guy, that's harder for the battery to push current through than if you were to throw extra lanes on here. So adding these extra branches and giving this battery more options means it's easier to push current out than it would be just through that guy. So this number should definitely right here be less than 2. As far as figuring out what it is, I'm going to rearrange that equation to say resistance is voltage over current. And now 24 over 22 is going to be some horrible decimal number like 1.09. All right, that's definitely not 2 divided by 6 divided by 4 or whatever. Remember, this is just a coincidence that the equivalent resistance wound up being 20 divided by 5. So over here, this is going to be kind of weird how we actually did this, and I'm going to show you on Tuesday, 4th period, Wednesday, 5th period, easier way to figure that out. All right, but for now, I want you to be able to do the first few problems on the University of Texas homework. You should be able to make your way up at least through number 11. All right, I'd love it if you all came into class having 1 through 11 done on that first University of Texas homework, the S versus P circuits. Thank you very much.